Okay, APers, let's continue talking about things that rotate, and in this case, a very special example. This is called the shape race. And the shape race takes place on a sloped board. So let's draw a big flat board like this, and it's held up at one end, a distance h, and we're going to put various shapes at the top, and we're going to let them roll to the bottom and see what happens. Now, the various shapes that we're going to use a solid sphere, and solid sphere has a moment of inertia of 2/5 mr squared. I need this other pen here. We are going to use a solid disk. And a solid disk has a moment of inertia of 1/2 mr squared. That's about the worst solid disk I've ever drawn. And then we're going to use a hollow hoop. Now let's see if I can draw a hoop type shape. There we go. In other words, a ring that has all of its mass concentrated at the outer edge, and rings have a moment of inertia of mr squared. And what we're going to do is we're going to put the various shapes at the top of this ramp, whatever shape it has, a circular cross section, and that's going to mean that it has potential energy. And what I want to do is find out how much kinetic energy it has at the bottom. But the kinetic energy is wrapped up in both channels: the kinetic energy of translation based on its velocity and the kinetic energy of rotation, because this is going to roll without slipping. Now, I submit that whichever of these shapes gets the highest velocity at the end of the ramp will win the race. In other words, if you start with 0 velocity and you have a higher velocity at the end, that means you had a higher acceleration the whole time. We can go back and do this another way, but I'm doing this little sleight of hand because I want to use energy to solve this. It is just so much easier to solve these problems using energy. Okay, so what's going to happen is we're going to say that the potential energy turns into a combination of translational and rotational kinetic energy. And m times g times h is the potential energy at the beginning of the problem. 1/2 mv squared is the translational kinetic energy, and 1/2 I omega squared is the rotational kinetic energy. Now we're going to do two things here for each of these. First off, we're going to put in the appropriate I for each shape. That's the first thing we're going to do. And number two, we're going to substitute for omega, we're going to put in V over R, because if it's rolling without slipping, this is the relationship between omega and V. So let's do all of our shapes here: the sphere, the disk, and the hoop. And let's see if we have enough room to do the calculation. Here we go. Okay, so using this as my starting point, mgh equals 1/2 mv squared plus 1/2 of 2/5 mr squared, that's the I, and then times omega squared, which is V over R quantity squared. Okay, we have m's everywhere, here, here, and here, so they cancel. So all that's left on the left-hand side is gh. Then here we have v squared over 2, 1/2 of v squared. And here, 1/2 of 2/5 is 1/5. R squared here, R squared down there, they cancel. The m's are gone, and so we got v squared, so we have 1/5 v squared. So we basically have v squared times 1/2 plus 1/5. Now, we have to go to tenths to get this done. 1/2 is 5/10, and 1/5 is 2/10. So that is going to be 7/10 v squared. So v is going to be the square root of 10/7 g times h. That's how fast the sphere will be going when it gets to the bottom. How about the disk? Well, mgh equals 1/2 mv squared plus 1/2 of 1/2 mr squared, and then v over r quantity squared. See, I'm just putting in what omega is, and I'm putting in what I is for a disk. Again, m's everywhere, they cancel, so all that survives on this side is gh. On this side, we have 1/2 v squared plus, now 1/2 of 1/2 is 1/4, and the r squareds cancel again, and v squared. So 1/2 plus 1/4 is 2/4 plus 1/4, or 3/4. So gh equals 3/4 v squared, and v is going to be the square root of 4/3 gh. Now, between these two, which is bigger, 10/7 or 4/3? Now, 4/3 is 1.33, and let's just see what 10/7 is. 10/7 is 1.42. Ooh, I should probably jot this down. So this is 1.42, and this is 1.33. So it looks like if we were to race a sphere versus a disk, then the sphere would get to the bottom first. I guess that kind of makes sense. The sphere has more of its mass concentrated near the center, and so less resistance. Let's see what happens with the hoop. M times G times H equals 1/2 mv squared plus 1/2 of mr squared times v over r quantity squared. Almost ran out of room there. Okay, m's cancel everywhere again, leaving gh on this side, 1/2 v squared on this side, and now 1/2 v squared again. So 1/2 plus 1/2 is 1, so v equals the square root of g times h. And that's got a coefficient in front of 1. So it looks like a sphere would win over a disk, and a disk would win over a hoop based on this analysis. That's the shape race. It's a lot of fun. And again, I pulled a little trick. Instead of finding the acceleration to figure out who was going to win the race, I went ahead and found the ending velocity and assumed that the ending velocity would indicate the acceleration. Now, if we wanted to find the acceleration, we would have to do something a little different. We would have to analyze the actual forces, and this is where we're going to start drawing what's called an extended body diagram. So let's take the disk as an example. Okay, what are all the forces on this disk? Now, a free body diagram used a dot to represent the forces on the disk, but we are going to be using arrows. So this obviously has weight, and as it starts to roll, there's going to be some friction here, which is going to cause it to spin. So how do we do this? Well, there's two different ways to do this. One is to use we probably need to use as an axis of rotation the center of the object here. So considering that, the axis of rotation. And that means that there's going to be some linear forces on this object. Friction, mg sine of theta, and mg cos theta. And I guess there's going to be a normal force as well, isn't there? But there's also going to be some torques about this object. Now, the normal force is acting right through the center, so the normal force does not produce any torque. The weight is acting at the center, so it does not produce any torque because those are no distance away from the pivot point. So the only thing that's producing torque is going to be friction. So the only thing producing torque, the only thing trying to spin this is the friction. And then that makes sense, the friction at the bottom that makes it start to roll. So we have two different things to say that are true here. We have that the sum of the x forces is leads to acceleration. So mg sine theta minus the friction equals m times our linear acceleration. We also know that the normal force will be equal to mg cos theta. These two are going to balance out, and we have a torque equation that the sum of all the torques, that means the frictional force acting at a distance 1 radius away from the axis of rotation, this is going to produce I times alpha. Okay, let's see here. We want to get acceleration. We want to get rid of friction. So I think that what we should do here is solve this for friction. Now, I we can replace with the actual moment of inertia of a disk, which is 1/2 mr squared. Alpha can be replaced with acceleration divided by r, and then there's r. Well, look at this. R squared divided by r is just r. Divided by r again is gone. So this friction is going to be 1/2 of the mass times the acceleration. Let's put that in up here. mg sine theta minus 1/2 ma equals ma. Let's get that to the other side. Well, first let's cancel out all the m's. Oh my gosh, look, they're everywhere. So g sine theta equals 3/2 a and 2/3 g sine theta equals a. Now, if we do this for all the other shapes, putting in the different moments of inertia for the other shapes, we'll get different accelerations, and we can demonstrate which one of these shapes would go have large acceleration down the ramp. And it should give us the same result, that the sphere is more than the disk, which is more than the hoop. Let's see if we can do this mentally. If we were to do this again for the hoop, this wouldn't be a 1/2, it would be just m times a. That would have gone in over here and been added. This would have been a 2 instead of a 3/2, so this would have come over as a 1/2 g sine theta equals a for the hoop. So this was the disk, this is the hoop. And then if we were to put in for the sphere, let's go blue for that. If we were to put in for the sphere, we'd put in 2/5. So this would be F equals 2/5 ma. We would have put that in here as minus 2/5, would have brought it over to the other side. Let's see, so that would have been 5/5 plus 2/5 or 7/5, which would have come over as 5/7 g sine theta equals a for the sphere, and 5/7 is bigger than 2/3, which is bigger than 1/2. So once again, by doing the analysis of the forces and torques. Now, this is the part that is, I think, new to us, and we're going to do quite a bit of this over the next couple of weeks, although we'll have to interrupt our thing to take an exam. But you analyze all the forces, and you have your Newton's second law in the y and x directions, but then you analyze the torques. Look for where these forces are being applied, and they cause a rotation of the object. And again, any force that goes through the axis of rotation or is originated at the axis of rotation does not contribute any torque, because there is no distance away from the lever, from the point of rotation. There's no lever arm is what I'm trying to say. So only the friction is actually causing the torque, causing the spinning. Okay, that's enough. That's enough for today.